Okay, now we're in section 9.2 where we're approximating the population mean mu using a confidence interval centered about x bar, the sample mean. Once again, I just want to remind you that you are only going to be expected to know how to do this on the calculator. The formula for this one requires the use of a table, which, as you know, I don't like tables, so we're going to go ahead and use the calculator to do this example. A Gallup poll of 547 adult Americans employed full or part-time conducted in August 2007 asked, how much total time in minutes do you spend commuting to and from work in a typical day? Survey results indicate that x bar equals 45.6 minutes and s equals 31.4 minutes. So remember that the population mean is probably not equal to the sample mean. We can almost certainly say that the population mean is not 45.6 minutes. However, it's probably close to that, as long as the sampling technique was done well, which is why a confidence interval is created around x bar, and the confidence interval will most likely contain the actual value of the parameter. So it says, construct and interpret a 90% confidence interval for the mean commute time of adult Americans employed full or part-time. So to construct this, we will go to Stat, Tests, and scroll down to number 8, t-interval. So at the beginning of the section, you read a little bit about the t-distribution. It's very similar to the normal distribution, except the tails are larger and the area in the middle is a little bit smaller. And the reason for that is it accounts for the fact that your S is also a statistic. You don't know the population standard deviation, so really we're using two approximations, and the t-distribution kind of makes up for that. Okay, so we select number 8, t-interval. Now there's two input levels, data or stats. We were given statistics in this example. We were given x bar and s, so we want to choose stats as our input, and then we type in the different stats. So we were given x bar, which is 45.6. We were given s, the standard deviation, 31.4. And we were given a sample size of 547. The confidence level here is 90%, so I'm going to put in 0.9. And then we go down to calculate. So at the top here, we have the interval. It's an interval notation. That's what these parentheses are. And then it kind of spits out the statistics for us. So let's write this down, our confidence interval. So I'll just round to one place because x bar was given as one place. So I have 43.4, comma 47.8. Okay, so we want to go ahead and write an interpretation of this. It's the same structure as before. We are 90% confident that the population mean commute time of employed Americans is between 43.4 minutes and 47.8 minutes. So the interpretation will always be like that. Just make sure you name the correct parameter in your interpretation. In this case, it was the mean that we were approximating. Part B, is it possible that the mean commute time is less than 40 minutes? Is it possible? Well, let me tell you right now, anything is possible. This is a 90% confidence interval. It is not a 100% confidence interval, and there's no such thing as a 100% confidence interval that you could construct. You could probably think of one that's ridiculous, like, oh, the mean commute time is between 0 and 1,000,000 minutes, but that doesn't give you any useful information. So is it possible? The answer is always going to be yes. It is possible. Is it likely? Well, no, because we are 90% confident that the mean time is between 43 and 48 minutes. So is it likely that it's less than 40? No, it is not likely. Right, so that goes ahead and answers that question. I want to do another example that uses the other input value, and that is using data instead of statistics. The following data represent the age in weeks at which babies first crawl based on a survey of 12 mothers conducted for Essential Baby. So you might think this is a problem because the sample size is very small. The sample size is only 12, but it does say here, a normal probability plot indicates the data come from a normally distributed population. So that takes care of that. Remember, the last requirement is either the sample size is large or the population is normal. So here they're telling us the population is normal. Construct and interpret a 95% confidence interval for the mean age at which a baby first crawls. So the first step, of course, would be to type the data values into L1. So we're going to go to Stat, Edit, 52, 47, 30, 37, 44, 56, 35, 26, 39, another 39, 26, and then 28. So all 12 are in list 1. Now we'll go to our T interval, so Stat, Tests, I think it's number 8, T interval. And now we're going to change our input to data. This saves us from having to compute X bar and S from the list. The calculator will do that all in one step. So now we want to change the confidence level to 0.95 because it's asking for a 95% confidence interval. Highlight Calculate and press Enter. So not only does it give us the confidence interval here, it also tells us the values of the statistics X bar and S, just for fun, why not? Okay, so let's go ahead and write down our confidence interval. Remember that this mean X bar is directly in between these two bounds because the interval is based upon this X bar value. Okay, so let's write these down. So the interval is about, let's say, 31.9 to 44.6. And then, of course, our interpretation. We are 95% confident that the population mean age mean age at which a baby first crawls is between 31.9 weeks and 44.6 weeks. So let's say once again that you want to create a confidence interval for mu, but you want a specific margin of error. You just have a desired amount of accuracy for your confidence interval, and you want to know what sample size is required. We do have a formula for that. Notice that this formula does not use the t-distribution because we can't find a t-value without a sample size. So we just do the best we can, and we go back to using the critical values z sub alpha over 2, which you will be given during the test. So let's go ahead and try an example of this. A researcher wanted to determine the mean number of hours per week the typical person watches television. Results from the Loney Statistics Survey indicate that S equals 7.5 hours. How many people are needed to estimate the number of hours people watch television per week? Actually, now that I'm looking at this, the formula is missing something. So let me go ahead and change that, and then I'll change that in my notes. Change this to, it should be the critical value times S over E. So you do need an estimate of S, which is the sample standard deviation. Okay, so sorry about that. I will try and fix that in the notes. A researcher wanted to determine the mean number of hours. So the first part A says within 2 hours with 95% confidence. So the within 2 hours would be our margin of error. The 95% confidence tells us that we need to use the critical value z sub alpha over 2 of z sub 0.025, which we've used before, 1.96. Okay, so we can go ahead and apply these into the formula. The S was provided above. So the sample size equals the critical value times the sample standard deviation divided by the margin of error squared. So we can go ahead and put that into the calculator. So I have 1.96 times 7.5 divided by 2 squared. Okay, now even though it's 54.0225, we still round up. For these sample size questions, you round up to the next whole number no matter what. Okay, let's try part B. Part B has the same confidence level, but the margin of error has decreased. Now they want a margin of error of 1, so they want a more accurate confidence interval. So let's see how that changes the sample size required. So for a formula that's only going to change the denominator, okay, let me see if I can do this, if I can get back my previous formula and then just change the 2 to a 1. There. So now I'm going to press enter to get the new sample size. Alright, that's quite a bit larger. So we're going to round that one up as well. So this kind of answers the question, what effect did doubling the required accuracy have on the sample size? The sample size increased greatly, almost quadrupled really. So we'll say it increased. Okay, let's take a look at part C. Part C is the same as part A as far as the margin of error, but the confidence level has changed, and that will change the critical value that we use in the formula. So if we're doing a 90% confidence interval, that means our critical value z sub alpha over 2 is the z sub 0.05, which you could get from your table. It's 1.645. I just remember that because I've done this a million times. And then the margin of error is the same as part A. It's 2. So let's put this into the formula. N equals the critical value, 1.645, times the sample standard deviation divided by the margin of error squared. Okay, so I have 1.645 times 7.5 divided by 2, and you square the whole thing. Okay, so it's 38.05. You need to round that up to 39. So we're being asked to compare that to part A. How does decreasing the level of confidence in the estimate affect the sample size? Well, from part A to part C, we were asked to find the sample size for a lower level of confidence. Notice that that lowered the sample size required, which makes sense. It's less accuracy, so you can get a smaller sample. So we can say the sample size decreased.